Hello students. So by now we have already discussed how the PN junction diode behaves under different biasing conditions. Uh, in no bias condition, in forward bias condition, and in the reverse bias condition. So basically there we discussed how the depletion region or the depletion width changes under different biasing conditions. So in each of the cases, the resulting diode current ID, the current through the diode, through the PN junction diode, is depending upon the bias voltage. That is, basically we are referring to by V subscript D, that is VD. P is at how much higher potential than N. So that is what we mean by diode voltage, and we denote it by V subscript D. So on the basis of how much we have applied VD, ID results to a certain level. So when VD was such that VD is no bias given across the PN junction diode, then ID means the net current is 0. When a reverse bias is applied, that is when VD is negative, we saw that the ID is mostly due to the movement of minority charge carriers, and it is equals to reverse saturation current IS for a very long range of negative VD values, that is for reverse bias voltages. And we saw that in the forward bias, that is when the VD is positive, when the VD is positive, the ID is mostly contributed due to the majority charge carriers, and so the net ID current is from P to N, that is from P to N side of the semiconductor diode. So that is the direction of the net current ID in the case of forward bias from P to N. Now in each of the cases we have the resulting ID depending upon the diode voltage VD. So remember every time that ID is the current through the semiconductor diode and VD is the voltage across the PN junction diode. That is how much is the P terminal of the PN junction diode higher than the N terminal of the PN junction semiconductor diode. And to establish this relationship between ID and VD, we have the diode equation, which says that the net current ID is equals to the reverse saturation current IS times e to the power VD upon NVT minus 1. Remember, there is a bracket over here. Okay, so IS is getting whole multiplied by e to the power VD upon NVT minus 1. So here VT is also expressed in voltage. Okay, it is in volts. So VT, which is expressed as Boltzmann constant K times temperature in Kelvin divided by charge carried by electron, which is 1.6 into 10 to the minus 19 coulomb. This is a measured value in volts, in terms of volts. So here e to the power VD by NVT. So here the numerator of the fraction is in volts and the denominator of the fraction is also in volts. Now we have now since we have an equation which relates ID with VD, we can plot the relationship. We plot this relationship in the in the form of a curve, and this curve, which basically relates ID with VD, is called as VI characteristics of the diode. VI characteristics of a PN junction diode. So what is this VI characteristics of a PN junction diode? It is the graphical representation of this very equation, which is the diode equation, the relationship between ID and VD. So this, when represented graphically in the form of a curve, so that will be called as your VI characteristics of a PN junction diode. Conventionally, in the VI characteristics of a PN junction diode, we represent the diode current ID in the y-axis, and the diode voltage VD is represented on the x-axis. So this is what the VI characteristics of a PN junction will look like in terms of axis. Now, how will the curve look like is basically depending upon the diode equation. The VI characteristic is nothing but exact graphical plotting of this particular diode equation. So before going to the exact plot of this diode equation, let us try to understand how is this diode equation behaving for different values of VD, for positive values of VD, for negative values of VD, and when the VD is 0. So if you'll see this diode equation, ID is equals to IS whole multiplied by e to power VD upon NVT minus 1. You can break this equation into two terms. If you multiply IS by this term and then this term. So if you do that, you have ID which can be expressed as ID equal to IS times e to power VD by NVT minus IS. So this is nothing but this very diode equation represented in an alternate manner. So this is the very diode equation only. Now for positive values of VD, when the VD is positive, that is for forward bias. So when the VD is positive and you have increasing values of VD, if you take values of VD, so you take successive values of VD which are larger and larger values. So as you go for higher values of VD, this varied term starts dominating heavily for this net ID current. The IS reverse saturation current is this second term is so very less as you move in the direction of increasing VD. In other words, I want to say that when VD increases, out of these two terms contributing to the diode current ID, this dominates, and this is so less in comparison to this first term, so that you can ignore this term. This term is negligible, is becoming negligible as you are going to increase VD more and more towards more positive values, more higher magnitude positive values. So in such a case, you can have assumption that for positive and increasing values of diode current, ID is approximately equals to the contribution made by the first term and very least by the second term, that is IS. So you can neglect it. So it doesn't mean that it is 0, but relatively when you compare the first term and the second term, the first term is getting very much dominating, so you can ignore the second term, that is minus IS. So for such regions, for positive and increasing values of diode voltage, you can assume or you can approximate the diode current is approximately equals to the reverse saturation current times e to the power VD upon NVT, that is contribution due to the very first term, because relatively for higher values of VD, as you move to higher values of VD, this IS has a lesser contribution, a far lesser contribution than the first contribution. So for higher values of VD, you can assume the diode current to be mostly due to the first term, and so approximated by the first term only, neglecting the relatively lesser IS. Similarly, for negative values of diode current, that is when VD is negative, okay, this was a case when VD was positive. Okay, now in the second case, when you take VD to be negative, the first term becomes very less as compared to this minus is term, the second term. The first term for negative values of VD is becoming very lesser, relatively very lesser as compared to minus S component. So for negative values of diode current, ID can be approximated as minus IS, which is the second term of the diode current ID. And you just you should give a special attention to this case, that is for forward bias, that is for PD when it is greater than 0. Okay, you can just relate it, you should see it uh, relating to this very relationship where y is equals to e to power x. So in an exponential relationship, when even for a small increase in x we see a large increase in y. Okay, such is the very relationship in a exponential function. So for very small increase in x, there is a large increase in y. As you will see here, the at x equals to 0, y is 1, that is e to power 0 is 1. When e to power 1, that is x is equals to 1, so when e to power 1 we have, it becomes 2.718. So for x equals to 1, y has become 2.718. Similarly, for x equals to 3, for x equals to 3, y has already become 20.1. For x equals to 4, we have y equals to 54.6. For x equals to 5, we have y equals to 148.4, and so and so. For small changes in x, we have very large changes in y in an exponential relationship. As you can see here, from e to power 5 it is 148.4, and here we have e to power 5.5, and we have already moved to 244.7. So as you go on for higher values of x, this curve has very much becoming vertical in nature. It is becoming very much vertical in nature. So keeping in mind the very nature that we have seen of the exponential function y of e to power x, we can see things for the diode equation for when Vd is greater than 0. Here we see Id is exponentially related to Vd. So we can expect the Vd, for a small change in Vd, we can expect a very large change in Id. So it will be quite relevant when we'll be seeing the forward bias characteristics of the diode in the Vi characteristics. So as per our expectation, here's what we are seeing here. So this is Vd axis of the Vi characteristics of diode. This is the diode current axis, Id, and this dashed curve represents the Vi characteristics of a PN junction diode according to the diode equation, that we have written down here. And this curve in this region, when Vd is greater than 0, okay, this is the curve. So when Vd is greater than 0, all these dashed points represents the forward bias characteristics of the PN junction diode for Vd greater than 0 according to this very diode equation. So here, as expected, for a small change in Vd, we are incrementing into a very large change in Id. So as expected, because of this expression approximation when Vd is greater than 0, and when Vd is less than 0, when Vd is less than 0, this diode equation can be approximated to this approximation of diode current, where ID is approximately equals to minus of reverse saturation current. So here for negative VD values, for here, so here for negative VD values, you will see that the diode current is in the direction opposite to the diode direction. Diode direction is this, but in the reverse bias condition, the net current is in this direction. So that's why the minus symbol is used here. Okay, it is to be seen here. So minus is to denote that the current is in the direction opposite to the direction of the PN junction diode, that is from N to P. The net current is in the direction of N to P, and the current's magnitude is equals to IS. So minus is to say that the direction is opposite to the diode direction, and IS is the magnitude, which is a constant for any particular diode at any temperature. At some constant temperature, IS for a diode is constant. So at a particular temperature, we are observing that when we are moving for higher and higher negative values of VD, as we are making the VD more and more negative in this direction, the ID has stuck or has saturated to the minus IS value. So IS being a constant, let's say here is the IS is 10 picoampere. So IS being 10 picoampere, even if we are increasing the VD in the negative direction, we are making the VD more and more negative, the ID is saturated to the IS or minus IS current level. So this approximation is reflected in the this VI characteristic when VD is less than 0. And you should pay attention that in the forward bias, we are increasing the VD in the graph. We are showing it increasing in tenths of volt. That means if this is 0, then this is 0.1, then this is 0.2, then this is 0.3, 0.4. So we are increasing from left to right in tenths of volts. Okay, so very small change in VD, we are very small steps are being taken to increase the VD, and still we can sense a very larger changes in the ID, which is quite expected due to this very approximation of diode equation in the forward region when VD is greater than 0. And in the VD less than 0, if you see the VI characteristics, we are increasing the VD in negative direction in tens of volt. Okay, here we are increasing in tenths, that is 1 by 10. But here when VD is less than 0, okay, for this portion of the graph, we are increasing the VD in negative direction in tens of volts. And even if we are making such large steps uh, in negative VD direction, okay, the ID current, we are seeing almost no change, because it is seen to be stuck, or it has saturated to the minus IS current level. So that's why only we are calling this level of saturation current as reverse saturation current, because it is flowing in the reverse direction opposite to the direction of diode. So that's why reverse, and it has saturated, so it is not changing with increase in VD in negative direction. VD we are making more and more negative, and still the diode current is not changing. So that's why the word saturation has been used. So that's why the nomenclature gets justified, that is IS being called as the reverse saturation current. Okay, so we are decreasing the VD, or you can say increasing the VD in negative direction, and still the reverse saturation current is saturated. If we are, it is observed saturated. What more is to be seen here is that this ID axis, that is Y axis, in which we are representing the diode current. The current 1, 2, 3, 4 like this up to 20 is expressed in milliampere. Okay, all these are 1 milliampere, 2 milliampere, 3 milliampere, 4 milliampere, and likewise. But below this zero, whatever negative currents we have represented in this VI characteristics, those are in terms of picoampere. Okay, so what is meant from this is whatever reverse current is going to flow through the diode in the reverse bias condition, those are very small currents, but because they are being contributed by the minority charge carriers. So for that reason, the reverse current is going to be very less for a great range of negative VD values. So mostly the current is the saturated current, which is reverse saturation current. So that is a very small current in picoamperes, and pico by peak saying pico, it is 10 to the power minus 12. So when we say 10 picoampere, that means 10 multiplied by 10 power minus 2 minus 12 ampere. Okay, 1 picoampere is equals to 10 to the power minus 12 ampere. So whereas here in this for forward bias conditions, whatever currents are resulting, those are expressed in milliampere. Okay, and we know that 1 milliampere is equals to 10 to the power minus 3 ampere. So milliampere is a larger current as compared to your picoampere, which is very small current, 10 to the power minus 12 ampere. So in the reverse bias condition, the current's magnitude is very less, whereas in the forward bias region, the diode current magnitude is very much higher. And I told you that this dashed line curve represents the VI characteristics of the diode according to the diode equation. Then what is this blue curve then represents? Okay, so this blue curve, as is written here, it is the actual commercially available PN junction diode, how the curve will look like. So the curve is slightly different than the theoretical curve. The theoretical curve means the curve corresponding to this diode equation. The actual curve for a commercially available PN junction diode will look somewhat like this. It has got a you can say the curve has been shifted to right, or you can say that the threshold voltage to turn on the diode is somewhat higher. So what is threshold voltage then? Threshold voltage is that voltage after which the diode allows a sumptuous amount of current through it, a considerable amount of current through it. So as you can see for this dashed line, dashed representation of the curve somewhere over here. So below this threshold voltage, the current levels were very less. Okay, but once this threshold voltage is crossed, when the VD is beyond this VT threshold voltage, the ID is increasing enormously. Okay, for a small value, small change in VD, the ID is changing enormously. So it is giving a sumptuous amount of current ID through the diode for these levels of VD. Okay, for let's say for this level of VD, the diode current is now not depending upon the diode itself, whether it is depending upon the circuit in which the diode is present. What are the other resistances? What is the DC power supply that has been used? It is now depending upon that. But before the threshold voltage, the diode's current is depending highly on the diode itself, and it is very minimal. So threshold voltage is that critical point after which the diode allows a sumptuous amount of current through it. So if you see this graph, which is for the diode VI characteristics, we have two curves. One is shown in the dashed line fashion, and another curve is shown in solid blue curve. So this dashed line curve is the graphical representation of this diode equation, which relates ID with VD, and this curve, the solid blue line curve, represents the behavior of the diode which is actually available in the market. So actually your the commercially available unit is in a slight manner different than the theoretical model of the diode. So what is the difference is that uh, practically available diode, okay, it has got some body resistance. It has got some body resistance of its own, and even they have got the contact resistances. So there are drops across the diode because of this contact resistance and because of the body resistance of the diode. So because of this voltage drops, a higher amount of VD is required to turn on the diode. Okay, to allow the same amount of ID requires a higher amount of VD. So that's why the curve looks to be somewhat shifted to right for the actual commercially available diode. Okay, and we also see a difference in the reverse saturation current, and that may have resulted due to the uh, higher temperature conditions in which the commercially available diode will be operated, or due to the doping levels. A higher level of doping will result into a higher reverse saturation current. Even this reverse saturation current is temperature sensitive. Okay, even for every 10 degrees Celsius rise in temperature for any particular given PN junction diode, the reverse saturation current IS doubles itself. So for every 10 degree Celsius rise in temperature where you are conducting the experiment, or where you are using the diode, the reverse saturation current will double. Okay. So as we have defined the threshold voltage VTH as that critical voltage, that critical VD value beyond which the diode current increases generously with smallest increase in VD. Okay, so that is called as your V threshold. So V threshold is also called as firing voltage, VF. These are the different names for the same critical voltage, which we have just defined it as that particular VD value beyond which the ID current increases enormously or generously for slightest change of VD. So before this critical VD value, the the diode current was not much sensitive to VD, but after this threshold voltage, this critical voltage VD, critical voltage of VD, which we are naming it as VTH, the diode current is very sensitive to a smallest change in VD. So after this, the diode current, the ID is now getting more and more controlled by the circuit in which the diode is present. How much DC power supply is there, how much other resistances are there in the circuit, that will only determine the level of ID through the diode. Okay, so beyond threshold voltage, the diode current is depending upon the circuit components rather than on the diode itself. But before threshold voltage, the diode current is depending upon the bias voltage, the biasing voltage of the diode, that is VD. Okay, so it is not much depending upon the circuit parameters or circuit components. So that is the significance of V threshold. So we can say that for actual commercially available unit, the threshold voltage is somewhat higher than the diode that is assumed, which is assumed to be following the diode equation.